Okay, good morning. So in the last class, what we have done is we have seen how, what happens to a wave that is propagating through a lossy material. So we have seen that when it propagates through the lossy material, as the name itself suggests, there will be a loss of amplitude. When I'm talking of amplitude, we are talking of the amplitude of the electric and the magnetic field. Okay. Additionally, there is a relationship between the amplitude of the electric field and magnetic field. The relationship is H naught equal to E naught by modulus of eta. Then we also found that the attenuation that is happening is denoted by the expression e to the power of minus alpha z, where alpha is called the attenuation constant. And then when you come to the phase difference between the electric and magnetic field, you find that there is a phase difference of theta, eta. Theta, eta. Theta, eta is the angular part of the intrinsic impedance. Okay, this was the summary of last class. After we completed that, we had gone to this expression sigma by omega epsilon. We saw that it was a ratio of the conduction current by the displacement current density. And we talked about this quantity tan theta. We called it loss tangent. A loss tangent is very small if it is a perfect dielectric. And if it's a perfect conductor, the loss tangent is very large. Okay. And after that, we saw that there is also a relationship between theta, eta, and theta. Theta is 2 times theta, eta. Now, after we have completed that, we are starting from here. Okay, so now what I want you to do is just look at the phasor representation of this equation. Obviously, you can see that this is modified Ampere's law. And here what you do is, we have just tried to take out, omega epsilon. If you take out omega epsilon out of the bracket, then you are left with sigma and j omega sigma into 1 minus j sigma by omega epsilon es. Now what we are doing is we are calling this term, what is written in red here, as epsilon c. We are calling it as epsilon c. What is epsilon c? Epsilon c is complex permittivity. For the first time, all along your life till now, you have always thought that permittivity is a real quantity. You had always seen that it can be 8.85 into 10 to the power of minus 12, or it can be 2 times, 3 times, some multiples of that. Okay, and you always saw that epsilon was a real quantity. It was not complex, but for the first time, you're seeing that epsilon permittivity can be a complex quantity, and it is denoted by the letter sigma with subscript c. And what is epsilon subscript c? It is epsilon into 1 minus j sigma by omega epsilon. Okay, or what we are doing is we are going to now separate out the real and the imaginary part. We are going to separate out the real and the imaginary part, and we are going to now write an expression: complex permittivity is equal to a real part plus an imaginary part. A real part epsilon prime and an imaginary part epsilon double prime. Okay, epsilon prime and epsilon double prime. Now, what is this real part? Real part is the sigma that you had known all along. That is the real part. That is the sigma that you always had studied. Okay, and what is this epsilon double prime? Epsilon double prime is sigma by omega. You can see from here it is sigma by omega. Okay, and if you just manipulate these two expressions, you are also able to see that the ratio of the complex permittivity to the real permittivity is also equal to the loss tangent, which is sigma by omega epsilon. So all these are related. And when will you come across complex permittivity? Permittivity will become complex whenever you're dealing with high frequency AC signals, because all along you have been talking of DC or at most frequencies which are used for transmitting power. Okay, but when we go to communication, when we go to high frequency, the dielectric is going to have two parts. It's going to have a real part, it's going to have a complex part. Then this part is not there in your book, but then I thought when you're studying this, you also need to know why you're studying this, where is it applied, what is the significance. Okay, so now what I will now write for you is Dielectric constant. What is dielectric constant? Dielectric constant is epsilon r. You must have seen, epsilon equal to epsilon r into epsilon naught. You have seen, this epsilon r, okay, which is equal to epsilon by epsilon naught, is actually also called the dielectric constant. Okay, and dielectric constant or relative permittivity epsilon r signifies the efficiency of the dielectric material to store energy, because I told you all these materials are essentially for storage of energy. So higher this value, better will be the energy storage. Next thing, as I told you, in AC fields only, you're going to see this stuff happening. Permittivity will be a complex quantity. There is an imaginary part, and the imaginary part is always positive, and it is associated with dielectric losses or losses due to Joule heat. Now, you're all electrical and EC students, you know that this is very, very important. So the imaginary part talks about losses. These losses are called dielectric losses. You must have heard of hysteresis losses and all that in your electrical sciences. So similarly here you have a dielectric loss which is signified by the imaginary part. Now, what is the significance of the real part? Let us look at the significance of the real part. When you're going to the real part is talking about the degree of polarization. That is not surprising for you, because when we introduced this dielectrics for the first time in physics, we saw that the dipoles are all randomly oriented, and then when you apply an external electric field, the dipoles will orient. How much of orientation of the dipoles happen? That is polarization. Okay, so the degree of polarization is actually signified by the value of the real part. Larger the polarization, larger will be epsilon prime. Okay, next. Let us also see what is the significance of this. The significance of the real part is energy storage. The significance of the real part is energy storage. Larger the real part, larger is the energy storage. Larger the complex part, larger is the energy losses. Okay, and finally, let us also understand. I told you that this imaginary part would not even be there for DC fields or low frequency. So that automatically means that the dielectric constant is a function of frequency. It's a function of frequency, and as the frequency of the electromagnetic wave increases, let us see physically what happens. What is the meaning of frequency? Frequency of a signal means the number of times the electric field will keep changing direction. The number of times the electric field changes direction per second. So that's the frequency. So if I'm talking of 10 to the power of 9 as the frequency, that means 10 to the power of 9 times it is going to keep changing direction. Okay, so what if you remember, you have studied polarization in the context of water molecules in physics. Okay, you've seen there that the water dipole will keep on changing direction. That is the basis for microwave cooking. Okay, but here what happens is, in the normal dielectric material, what happens is when the frequency keeps going up, the dipole is not able to keep pace. Okay, the dipole is not able to keep pace with the frequency. Therefore, the value of the dielectric constant or the polarizability decreases, and the value of the dielectric constant, because of the polarization mechanism, will decrease. Okay, so the dielectric constant has got something to do with frequency, and the real part is not able to keep pace with the high frequency. So therefore, if you see how the dielectric constant changes with frequency, you will see that initially it will increase, and then after a certain frequency it starts decreasing. So these, whatever I have told you, they are all research topics on which people are currently working. Okay, and these have a lot of applications in your fields. I am, as a material scientist working in this area, I am just talking about what is happening in the field of research at the material level. Application level, you as engineers should look for applications. Okay, essentially it is for energy storage. Okay, so now we have completed lossy dielectrics. Now we have to move to lossless dielectric or perfect dielectric. Please remember, whenever I say perfect dielectric, I'm talking of lossless dielectric. No conduction happens. Epsilon will be 0. Okay, and then of course you can also additionally see that Okay, because conductivity is 0, sigma will be much less than omega epsilon. Okay, so now what we'll do is, let us take our basic equation for alpha and beta. Let us take our basic equation for alpha and beta, and into that, for this expression, okay, you can see that sigma becomes much less than omega epsilon, means this becomes negligible. This becomes negligible in both these places. This part becomes negligible. Once this is negligible, what happens to alpha? Mu epsilon under root of 1 minus 1. So what will you get? 0. Alpha will become 0. Now come to beta. Here what happens? 1 plus 1 will become 2. And denominator you have a 2. So 2 and 2 will go. So you will be left with beta equal to omega under root of mu epsilon. Okay, so you have got a new value for, you've got two new expressions, one for alpha and the other for beta. And this is when the wave is going to pass through a lossless dielectric. And what is the significance of alpha being 0? What was alpha? Alpha was attenuation constant. So when I say that alpha equal to 0, what I'm trying to say is that there is no attenuation. Straight from mathematics, you've got that when a wave travels through a lossless dielectric or a perfect dielectric, there will be no losses. Whereas when it is a lossy dielectric, what happens is, I told you the other day from SPM, you are having crystallites of conducting material also. So what happens at the boundaries? There will be scattering of waves happening. Scattering leads to losses. So that's the reason why there will be losses there. Whereas here there will be no losses. And you've got a nice expression for beta. Beta is omega into under root of mu epsilon. So therefore, you already know the expression for propagation speed as omega by k or omega by beta. Okay, therefore, when you use it here, you will get 1 by under root of mu epsilon. So you can remember this by using the expression for the speed of light in vacuum. Speed of light in free space. What is that? 1 by under root of mu naught epsilon naught. So I'm just trying to tell you ways of remembering. Next. Also immediately you know the relationship between wavelength and beta, or wavelength and k vector. It is 2 pi by beta. So just substitute. So you get 2 pi by omega under root of mu epsilon. Okay, I'm just going fast because there is really nothing much here. Next, let us come to the basic expression for eta. This was the expression for eta that we have seen last class. Now, if this fellow becomes 0, j and j will get cancelled, omega and omega will get cancelled. Therefore, you will see that eta becomes real. Intrinsic impedance becomes real, and intrinsic impedance will be equal to under root of mu by epsilon. Okay, so what are the things we have seen? We have seen that c is 1 by velocity is 1 by under root of mu epsilon, and eta is under root of mu by epsilon. And you're not having any imaginary part, therefore angle is 0. So this means that theta eta is 0. This means that theta is 0. Okay, and what is the significance of all this? Lost tangent is 0. That's what I told you in the last class. I told you in the last class, okay, lost tangent will be 0 for a real perfect dielectric. So that's what you are seeing. Okay, and what is another thing that will come out of this? Another significant thing that will come out is that you've seen in the last class that theta eta will get into H. You've seen in the last class that theta eta will get into the phase part of H, and you would have written it as minus theta eta. But now theta eta is 0. So what does that mean? There is no phase difference between electric field and magnetic field. There is no phase difference between electric field and magnetic field. You see here. Whereas in a lossy material, what was happening? There was a phase difference. Okay. And that's what is indicated by the figure here. You can see that a wave is propagating along the z direction. Along the x direction, the electric field is varying sinusoidally. And along y, the h vector is changing sinusoidally. But you're seeing that corresponding to maximum h is the position for maximum E. And whenever h becomes 0, E becomes 0 at the same point. Or as the wave is traveling along the z-axis, okay, the electric field and the magnetic field are in phase with each other as long as the material is lossless dielectric. And next, you have also seen the relationship between E naught and H naught. H naught is equal to E naught by modulus eta. And modulus eta now you know is under root of mu by epsilon. So the conclusion here is beautiful and simple. It just says that the wave propagates in a lossless dielectric without attenuation. That's the first point. Next thing is electric field and magnetic field are in phase. That's why we said that if you finish your lossy, then everything else will become special cases and we can do it very simply. Okay. Now, once this is over, let us go to free space. What is free space? Free space is simply, free space is a special case of, free space is a special case of lossless. Why am I saying it's a special case of lossless? I'm saying it's a special case of lossless because you can already see that sigma equal to 0, lossless. Next, special case because in a general situation, you wrote epsilon and mu are not epsilon naught and mu naught respectively. But when you come to free space, epsilon equal to epsilon naught, mu equal to mu naught. So what should you do? You take your lossless equations, take all the lossless equations. Wherever mu is there, put mu naught. Wherever epsilon is there, you put epsilon naught. That's all we have to do. So look at this, alpha equal to 0, same. Next, come to beta. Beta we have seen was omega into under root of mu naught epsilon naught, mu epsilon. Here it becomes mu naught epsilon naught. And what is that? That is 1 by c. So omega by c. Now similarly, propagation speed. Propagation speed will be 1 by under root of, propagation speed will be under root of mu naught epsilon naught, which is going to be c. Okay. And lastly, let us come to lambda. Lambda will be 2 pi by beta. Okay, that is also holding good. And of course, when you substitute, you will get C by F, which is what you had used for light waves all along from your school days. And this is also a proof. All these equations go to prove that light is also a transverse electromagnetic wave. Only thing is its frequency is such that you are able to see it. Okay, so light is also part of the electromagnetic spectrum and it manifests itself as a transverse electromagnetic wave. Okay, now to complete. Eta. Eta we have seen for lossless was under root of mu by epsilon. So what will it become now? Here it will become mu naught by epsilon naught. And because it is for a free space, we will call it eta naught. Okay, and if you substitute the values, you don't have to every time in an examination, don't keep sitting and writing mu naught equal to 4 pi into 10 to the power of minus 7 divided by 8.85 into 10 to the power of minus 12. No, you don't have to do all that. Now you're engineering students, you have to just remember simple things like you will get 120 pi. You will get 120 pi as the intrinsic impedance of free space, and which if you substitute for pi will turn out to be 377 ohms. Okay, and theta eta is 0. Now finally, when you write the equations, what will happen? It's the same. E naught cos omega t minus beta z along the x direction means h will be along the y direction, no phase difference. Instead of h naught, you can write E naught by modulus eta. And how do I get this ay? I get this ay from this famous relationship that we have seen all of last chapter. Okay, so now what do you conclude? When a wave travels through free space, there is no attenuation. Electric field and magnetic field are in phase, and the wave will travel at the speed of light. It will travel at the speed of light. There is no dependence on omega because after all you have seen that u equal to 1 by under root of mu epsilon. There is no omega coming into picture. And in this case it is omega naught mu naught. Therefore any electromagnetic wave traveling through free space will travel with the speed of light. Okay, I can ask you questions like this in an examination. I can give you one frequency, tell you that the speed is something. I double the frequency. What is the speed? Okay. I have not asked this question in tomorrow's exam. Okay. Now we have finished 3 cases. How quickly we finish, you see. Lossy, lossless, and free space. Now let us come to conductors. This will be slightly different. Okay. How do you write the constitutive parameters for conductors? Let us look at the constitutive parameters for conductors. When you write the constitutive parameters for conductors, and you're talking of good conductors, so we presume that sigma is infinity, or resistivity is 0, and epsilon is epsilon naught, and mu is equal to some mu r into mu naught, and this expression is important. Sigma will be much greater than omega epsilon, much greater than omega epsilon. Now remember this, sigma much greater than omega epsilon. Now what I will do is, I will take you to a previous expression for alpha and beta. Let us go to the previous expression for alpha and beta. Now come to this expression, the basic expression, and think of sigma by omega epsilon becoming very large. Because sigma is very large, sigma by omega epsilon will be very large, or sigma by omega epsilon will become much greater than 1. Okay, or this +1, -1, all this will simply be disappearing. They become insignificant. And if these ones start getting insignificant and disappear, then what will be alpha and beta? Alpha and beta will become equal. Alpha and beta will become equal. So after we do that, let us get the expression, the basic expression for alpha and beta. Let us get the basic expression for alpha and beta. You will find that alpha is going to be equal to beta for a perfect conductor. And if you just go there and work out, you will get alpha equal to beta equal to under root of omega mu sigma by 2. And what is omega? Omega is 2 pi f. Therefore, you will get a simple expression pi f mu sigma. Pi f mu sigma. Okay. And what is u? U is the same expression, omega by beta. So all you have to do is just substitute for beta. Similarly, lambda is equal to 2 pi by beta. There also substitute for beta. Okay. Now let us go to eta. Eta, which is the intrinsic impedance. Take the basic expression. Now what will happen is we are going to neglect this part. Whereas in the previous thing, we neglected sigma. Now we are going to neglect this. When you neglect this, you will end up j omega mu by sigma. Okay. And under root of j, I have just shown you here. I've shown you here. Under root of j, okay, can be written as 1 plus j by root 2. 1 plus j by root 2. This is simple mathematics. I don't have to show you. Or you just take that 1 plus j by root 2 and square it and see. Then you will get j. Okay. So the final expression for eta will be, this becomes the real part. This becomes the real part. Okay. And the imaginary part is going to be, you can see here that the real and the imaginary part are equal. And whenever the real and imaginary part of a complex term becomes equal, you know that the angle is 45 degrees, because cos 45 and sin 45 have the same value. Therefore, the phase difference becomes 45 degrees, okay, or pi by 4 radians. Where does this happen? This will happen only when an electromagnetic wave is going to meet a conducting medium, a good conducting medium. So when it meets a good conducting medium, you will find that there is an eta, there is an attenuation. You see here, alpha is equal to beta. So that means there is an attenuation. And you are seeing that there is an angular part, 45 degrees or pi by 4. So that means two things will happen. One is, when a plane wave is incident on a perfect conductor, it suffers attenuation. So that's the first thing. The second thing is, there will be a phase difference between the electric and the magnetic field. Electric field will always lead the magnetic field by pi by 4 radians. That's a constant when it is a conductor. Whereas when it is a lossy dielectric, that lead will depend on the properties of the material and the frequency of the wave. Okay. Okay, now let us finally write the final expression for the electric and the magnetic field. E is equal to E naught e to the power of minus alpha z cos of omega t minus beta z along x cap direction. Therefore, H will be H naught e to the power of minus alpha z cos of omega t minus beta z, and the theta eta has become pi by 4. And minus, please remember, it will be always minus. Okay, now, so you conclude that when a wave travels in a conducting medium, its amplitude will get lost, or there is an attenuation depending on e to the power of minus alpha z. Now we do something more than what we have done for a lossy dielectric. Okay, in a lossy dielectric we left it and we said that it can pass through the material, but its amplitude will keep decreasing. Okay, but when it comes to conductor, things are going to be slightly different. Okay, so here, what is the difference? Let us say. Let us say that this is a conducting block. Okay, and when a wave is incident, what happens is alpha will be so large. Alpha will be so large that, okay, when Z becomes equal to 1 by alpha. I'm saying alpha will be large. For a conductor, alpha will be, attenuation constant will be large. Therefore, when Z becomes 1 by alpha, because alpha is large, Z is small. Okay, Z will be small. So when Z becomes equal to 1 by alpha, you will get e to the power of minus alpha Z as e to the power of minus 1. E to the power of minus 1. Or when a wave enters the conductor, it will only be able to enter to a small distance, and once it enters that small distance, what happens is it will get attenuated to 1 by E times the initial value at the surface. Okay, that means very quickly attenuation will happen, and this distance that we have written corresponding to Z equal to 1 by alpha, that distance Z equal to 1 by alpha has got another name. It is denoted by delta. It is denoted by delta, and this delta is called the propagation distance delta. It is called the propagation distance delta. So when you have a block of conductor, if you allow a wave to enter, it will lose its amplitude to 1 by E as soon as it has entered and gone through a distance called Z equal to 1 by alpha, and Z equal to 1 by alpha is called delta, and delta is the propagation distance. So what is the meaning of propagation distance? Propagation distance delta is the distance at which the amplitude will decrease to 1 by E. 1 by E is 37%. 37% of the value at the surface. Okay, and there is another name for delta. Delta is also called the skin depth or the penetration depth. It is called skin depth or penetration depth. And I said Z is going to be small, delta is going to be small because alpha is large. Okay, so you can show that delta equal to 1 by alpha, and that is the depth into which you can practically consider that the wave is entering. After that, what happens is, it becomes so small that you can practically say that there is no transmission happening, and you're calling it skin depth. Skin itself means thin. It's called skin depth because within a body, if you try to send an electromagnetic wave, it's only able to enter a small distance, delta, called a skin depth, and beyond that it is not going. So that is the difference between lossy dielectric and a conductor. In a good conductor, electromagnetic wave will not be able to penetrate and travel. It will go only through a small distance. Practically, we'll call it as skin depth. Beyond that, the amplitude will be very, very small. Okay. So it is as if electromagnetic waves get reflected from the surface of conductors. Electromagnetic waves get reflected from the surface of conductors. It can only enter through a small depth. Okay, so what is skin depth? Skin depth is the measure of what is the depth to which electromagnetic wave can penetrate inside the conductor. And we can take this concept for other things also. So we can say that skin depth is a measure of depth to which the electromagnetic wave can penetrate in a medium. And you saw that delta equal to 1 by alpha. Already we got the expression for alpha for a conductor. Okay, so just substitute that here. Just substitute that here. So look at this beautiful thing you are getting. You are getting that delta is inversely proportional to 1 by root f. Delta is inversely proportional to 1 by root f. Larger the frequency of the wave, smaller will be the skin depth. So skin depth depends on the frequency of the wave and the constitutive parameter mu. It also depends on the constitutive parameter mu and sigma. It doesn't depend on epsilon, it depends on constitutive parameter mu and epsilon of the medium. Okay, so here is a graph showing you, so this is the surface of the conductor. Or let me say that conductor is Z greater than or equal to 0. And here let us say you have some free space. So when a wave enters, what happens? Initially it is having an amplitude E0, but quickly that amplitude falls to 37% of the initial value. And what is the depth at which this is happening? This is happening at a depth of delta or the skin depth. Now for you to understand what will be skin depth, here is a table given to you for copper. Okay, for copper sigma value is given, mu is given. Okay, and you can see that for a frequency of 10 hertz, it is able to enter about 20.8 mm. Whereas when you go to high frequencies, you see 6.6 into 10 to the power of minus 3 mm. So that means it is micrometer. And when you go to 10 to the power of 10 hertz, it is 10 to the power of minus 4 mm. You can see that it is practically not entering. It is just going to get reflected from the surface of a metal. So that's the important takeaway in today's class. Any doubts, guys? Any doubts? Okay, so now going ahead, the next page that I'm showing here is nothing, no new electromagnetism you're studying. All you're doing here is writing things in terms of delta. You know, eta equal to, this is, what is eta? This is your alpha expression. So when you just put it here, you're getting eta equal to alpha by sigma under root of 2j, which is 1 plus j by sigma delta. Wherever you're going to see a 1 by alpha, put it as delta. Put it as delta. Additionally, you know that metals, conductors also have alpha equal to beta. Therefore, you can say that for a conductor, alpha equal to beta equal to 1 by delta. Alpha equal to beta equal to 1 by delta. So here 32A and B are simply electromagnetic fields, electric field and magnetic field in terms of delta, nothing new. Wherever you had, say like for example, you come here, like for example, you come here, E0, what should you have had here? E to the power of minus alpha Z. Instead of alpha Z, you write Z by delta. Similarly, here you should have omega t minus beta Z. Instead of beta also you can write 1 by delta, because after all alpha equal to beta. And then of course this minus pi by 2, pi by 4 which appears for magnetism doesn't change. Okay. Next, what is the importance of the skin effect? Why? What is this phenomenon and what are the applications? Let's see. So what is skin effect? Skin effect is the rapid decrease in the field intensity on the surface of conductors. Okay. And so you know that there can be no current when there is no field. You all know that, right? No current when there is no field. Okay. So this also means that both fields and associated currents are confined to a thin layer on the surface of a conductor. Look at this. Here, please, this is not a wire. This is a cross section of a wire. This is a cross section of a wire. Okay, and let us say you are passing a current. Let the radius of the wire be A. So when you are passing a current, what happens is the current is not going to be there for the entire. So this is a current associated with the field. So what happens is it is confined to a small thickness delta on the surface. Okay. And please remember, then you will say, man, then how did we all along in physics? That means you taught everything wrong to us. We took the area of the conductor, the area of cross section, and then we said current divided by area is the current density. So that means you taught something wrong. No, I taught everything correct only. There it was DC. There it was DC. When it is a DC current, the current is there through the volume of the wire. Whereas now we are talking of AC. So when you're talking of AC signals, what happens is at high frequencies especially, the entire current will flow on the surface. Entire current will flow on the surface of the conductor, not inside. Guys, are you understanding this point? Revant?
Ma'am.
Yeah. Are you understanding?
Yes, ma'am.
Yeah. So that is a big difference. Till now, electrical science also you were talking of low frequencies or DCs. Okay. And similarly in physics also you talked of low frequencies. Low frequency also we didn't talk. We talked of DCs. Whereas now we are talking of high frequency. So whenever you're talking of high frequency application, current is confined to only the surface of the conducting wire, or it is confined to a small thickness uh, called the skin depth. So what are the advantages? Where do you use this? Okay. Now, you know that silver is a costly material when compared to other metals. Okay. But what happens is silver has got some excellent properties like wonderful conductivity. So what happens is you are going to, in a short time, you're going to study something called, the last chapter is going to be something called waveguide. Okay. You can pass your signals through waveguide. Microwave signals will pass through waveguide. Waveguide is used. So when you are passing through waveguides, very little loss should be there. Very little loss should be there. So for that, what they will do is silver is the preferred material. Okay, silver is the preferred material for a waveguide. For a waveguide, okay, silver is the preferred material. Okay, now what happens is if you have to make the entire thing with silver, it becomes costly. Okay, so what is done normally is you will use brass. Brass is not costly. You will use brass as the body and you just give a coating of silver inside. Okay, the wave is not going to understand whether it is pure silver or whether it is coated silver because it is not going to go beyond the thickness of delta. So you give a coating which is of the thickness of delta or a little more than the thickness of the penetration depth or skin depth of silver. So this is how you can bring down the cost. Instead of using pure silver components, you use silver plated components. Okay. And then second thing, all of you who have seen a television antenna, I'm sure all of you, at least in your childhood, when your fathers went up to the terrace and saw, I don't know whether your generation did that, aligning, at least my generation did that, aligning the antenna at the top of the roof. Okay, and if you see antenna, you must have seen that antennas are always made of hollow tubes. How many of you have seen this?
I did, ma'am.
You've seen it?
Yes,
Okay.
ma'am.
So antennas are made of hollow tubes. You can bring down the cost, mostly made of aluminum. You can bring down the cost and you can bring down the weight. You don't have to use solid conductor. Why you don't have to use solid conductor? Because the signal is not going to penetrate beyond the skin depth. So that's the reason why hollow tubes are used. Next, you have heard of shielding. Okay, shielding especially has to be done when you're doing high AC frequency experiments or high AC frequency devices have to be protected. You have to give electromagnetic shielding. So what is electromagnetic shielding? Electromagnetic shielding is put your device inside a metallic casing. Put your device inside a metallic casing. So what happens is anything outside or anything inside cannot communicate with each other. As long as the frequencies are large, they cannot communicate with each other because the thickness of this, if it is of the order of delta, it is not going to allow any communication. So this is how electromagnetic shielding works. Okay. And you must have seen the shielding even in your cables, which are coming to your from the antenna to your television or from your Wi-Fi. You must have seen shielding. The shielding also works on this principle only. It's not going to be able to communicate outside. You use electromagnetic shielding. And of course, you're going to also study something called AC resistance. And this AC resistance is completely because of skin effect only. Think of it, yeah. You have a tube, okay, of certain radius A. You're passing a current I, DC current or low frequency. It will pass through the entire area of cross section. Now the same current, think of a high frequency. So what will happen? What will happen? The material is not going to fully allow it to conduct. Only a small area, small thickness delta is available. So the effective area of cross section becomes very, very small, very, very small. So that means the resistance of the material is no longer a constant. It is going to depend on the frequency of the wave. It is going to depend on the frequency of the signal. So there is something called AC resistance. Till now you studied DC resistance. Like that you can talk of AC resistance. And AC resistance you will be able to see because of skin effect only. Guys, are these applications clear? Any doubts?
Yes, ma'am.
Yeah. Okay, now finally, before 2 minutes, I'll take to complete this. Okay. So let's say I have a wire. I have a wire, okay, and the area of cross section is S, okay, and let sigma be the conductivity of the material. Okay, from your school days, you studied that resistance is going to be, and if L is the length of the conductor, okay, then you know that the resistance for small frequencies or for DC, you studied this in physics, it is L by sigma into S, where S is the cross-sectional area. Or you must have studied this in physics as rho A by L. How many of you remember that? Resistance was rho A by L. Okay, so it is just that only, but here you're writing in terms of conductivity. So resistance is going to be L by sigma. Yes. What is S? S is the cross-sectional area. So this is the expression for, so that means the current is going to pass through this entire cross-sectional area. Okay. Now we are going to define something called skin resistance. Please guys, again, I want to caution you, skin resistance or surface resistance is not the same as AC resistance. Okay. So let us now talk about what is skin resistance. Skin resistance is defined as the real part of intrinsic impedance. The other day when I talked about intrinsic impedance, I said it is ohm. Impedance is a resistance. So it is, unit is ohm, I said. And intrinsic impedance is going to have two parts. It has got a real part and it has got a imaginary part. Now this real part of intrinsic impedance is the skin resistance. It is the skin resistance. This real part of intrinsic impedance is called the skin resistance. So because you already know the expression for delta, you can show that it is pi f mu by sigma. That means the skin resistance depends on the frequency. For a given metal, it depends on the frequency. Larger the frequency, larger will be the skin resistance. Why? Think of the logic. Larger the frequency, smaller will be delta. That means the effective cross-sectional area available for the current is small, larger resistance. Okay. Now we also talk about a third resistance. This third resistance is called AC resistance. This AC resistance depends on RS, okay, and it is, okay, this expression I'll try to first explain. I have a conductor, okay, of cross section S, of cross section S, and let the length be L and let sigma be there. Okay, now because it is an AC signal, what happens is the current is not there for the entire cross sectional area. Current is only going to be confined to this depth delta, to this depth delta. Okay, so the effective area through which it can pass is going to be small depth or small area only, which if it is a wire, I can write it as 2 pi W, I mean, I can say 2 pi A into delta, I can call it. That area can be called as 2 pi A into delta if A is the area of, A is the radius. Okay. So that is going to be actually the area available for the current to pass. Now, keeping this in mind, here is a picture. Here is a picture of a block, of a rectangular block. Okay. Let the length be L. And when I'm passing a current, what happens? Let W be the width. If I pass a current, the current can be confined to only this area, okay, area delta into W. It can only be confined to the area W into delta. Therefore, RAC will be, instead of writing L by sigma into S, for DC you wrote L by sigma into S. S was the total cross-sectional area. Here you will write L by sigma into delta W. Delta W. And then you can just combine these through 2 and show that RAC equal to RS into L by W. RAC and RS are related to each other. Okay. And there is no frequency involved in the relationship between them. It's only the dimension that is coming into picture. Here I have shown you for a conducting wire. Okay, if it is DC, the entire cross section is going to be involved. So therefore, S is equal to pi A square if A is the radius. Okay, whereas when you're talking of high frequencies, what happens? The current is just confined to just this small annular ring area only. So what is that annular ring area? The annular ring area will be 2 pi A into delta. A is the radius. Okay, so this is for AC. And now if you compare these two, what do you say? RAC will be much, much greater than RDC for high frequencies. Okay, whereas for low frequency or for DC, it is 1. Whereas RAC by RDC will be A by 2 delta or A pi F mu delta by 2. This is the ratio of the two resistances for high frequency. So actually, you can measure delta by carrying out the AC resistivity studies and DC resistivity studies. By just performing 2 experiments, you can calculate your delta. So RAC is much, much greater than RDC for high frequency signal, as delta is very small for high frequency. Okay. Now, this part I will do in the next class. It is just 2 minutes, but still I will do that in the next class. All this is not there in tomorrow's test. Okay. So I will do this part in the next class. And here I have put a table for you. I just put a table for you. Okay, so what is this table? I have just made a comparison between lossy, lossless, free space, and good conductors. All the equations that you will ever have to use are all tabulated for you, just making your life easy. So initial days when we work out problems, keep this table as your reference and keep working out problem. Then by the time you do 2-3 problems of each category, you will be thorough. Don't worry, it's not going to be difficult. Initially, it all looks so mind-boggling, and I have actually tried to reduce the pain by conducting this quiz tomorrow. Because now the quiz means you just concentrate on the concept and those equations. The concept and these equations, just go through that. Okay, and try to see the relation. If it's difficult for you to remember, you have to remember things like, it is the delta is proportional to 1 by under root of f. These kind of things, if you remember, then it is, or it depends on mu, sigma, and f. Like this, few things, if you remember, those equations will be easy for you to follow. But please, tomorrow's test is going to be understanding plus a lot of memory. Understanding plus memory. Okay, it's not numericals, it is only this part. Clear, guys?
And what is the portion for tomorrow's quiz, ma'am?
Portion is this till
This
what
chapter.
I have done now. Yeah, this problem till what I have done now.
Cumulative or only this 10th chapter? 10 chapter
only
from
10
start to.
chapter. I'm talking about not test, I'm talking about tomorrow's quiz.
Yeah, tomorrow's quiz only, ma'am.
Yeah, tomorrow's quiz only this. I want you to learn all these terms. You should know them by tomorrow. And from Monday, we will start working out numericals for all these concepts. Once we work out numericals, things will become more clear. Guys, what's happening? Any doubts? Sri Chakra?
No doubts, ma'am.
No doubts. So what is left is only for you to study. Ben Anna, any doubt?
Yes, ma'am.
Doubt?
No, ma'am. I have to study.
You have to study and you are not at all studying.
For this course, yes. ma'am.
Tomorrow's quiz is double the weightage of the other quizzes. Please remember, 20 marks. Because this much you have to study and write a quiz means it is worth giving. And last week I didn't conduct any quiz, no. So that's the reason why it is going to be 20 marks, 20 questions, please. Don't neglect, you will lose a lot if you neglect this. And this is the only place where I can catch you by the neck and make you study.
Lossy medium, ma'am.
Lossy medium?
This 20 marks is going to be a lossy medium for me.
If it is going to be a lossy medium, then this entire paper is going to be a lossy medium for you, my dear. If you learn this up, then what comes ahead will be very, very logical and simple. If you don't learn this, I cannot help you. Write and see. Keep writing. If it is a lossy medium, I'm telling you the entire paper will be a lossy medium and all of you will lose your CGP also will become a lossy medium. This is a basic paper for your other papers. That also you remember, guys. Okay, so assuming that everybody has understood, I am going to stop my what do you call my recording. Okay, best of luck for tomorrow's